Okay, this is our last video for the topic valid and invalid arguments. And for this last video, we're going to consider arguments for which the premises are not in the form that uses connectives like P implies Q, P and Q, or P or Q. Instead, we have here arguments for which the premises and the conclusion are expressed using quantifiers. Quantifiers are those phrases that normally appears in the statement, like all, every, none, no. Those are what we call universal quantifiers. Then there's another type of quantifier called as existential. Those are quantifiers that uses some, there exist, okay, and so on and so forth. So you will notice here that the argument we have in this example, are the arguments or the premises are in the form that uses quantifiers, okay, for the statement. Now, before we determine whether this argument is valid or invalid, we will use the Euler diagram as our guide for that matter. Okay, this is the Euler diagram. This is actually similar to the Venn diagram, okay, where you have the square or rectangle and sets are placed inside that rectangle. Okay, and these are statements that are expressed using quantifiers. So what do we mean by the statement all x are y? So when you have all x are y according to the diagram, it means that x is a subset of y, okay, or x is inside y. So all x belongs to y, right? Okay, that's what we mean by all x are y. Or you can also express that as every x is a y, okay? So same idea. Another statement here is the statement that says no x are y. It means that you have two sets which are disjoint. There's no intersection. So no x are y. In other words, a particular element of x is not found in y. The third case is the statement some x are y. This time it uses existential quantifier. By the way, the all, the every, the no, the none, are called as universal quantifiers. Okay, for some x are y, it means that the set x and the set y have a common region. Okay, so this is what we mean by some x are y. If that here belongs to x and belongs also to y, that means that they are not disjoint. So there's a common point or common element between the two. And when you say some x are not y, it means that x and y have a common factor, but there is one particular element that belongs to x but does not belong to y. In particular, this dot here, which is, although it belongs to x but it does not belong to y. So that's what we mean by the statement some x are not y. Okay, and using this as our guide, let's consider our first example. Okay, we will refer to the diagram from time to time. Okay, so the idea here is you have to construct the diagram, Euler diagram, for this argument, and based on the premises, and then from the diagram that you have made, you have to check whether your conclusion is consistent with that diagram. Okay, so let's start with the first premise. So draw a rectangle here, and then you say all mathematicians are logician. So when you say all mathematicians are logician, it means that you have a set of mathematicians, okay, and then you have a set of logician where the set of mathematician is inside the set of logicians, right? Okay, from our diagram here, all x are y, so all mathematicians, so this is the set of mathematicians, while this one, the bigger set, is the set of logicians. Okay, that's for your first premise. Now your second premise is Ethan is a mathematician. Okay, that means that that's a single point actually. That's a single person. So we represent that by a dot. Okay, that's Ethan. Okay, Ethan is a mathematician. That must be inside the set of mathematician. No? Okay. Okay, so this is the diagram representing the two premises. Now look at now your conclusion. Is your conclusion consistent with this diagram? Is it true that Ethan is a logician? Meaning, is it true that Ethan, which is represented by that dot there, is inside the set of logician? Yes. That particular point that belongs to the set of mathematicians also belongs to the set of logicians. So, since your conclusion is consistent with the diagram, then you say that the argument is valid. Okay? So, that's how to determine whether the argument is valid or not valid whenever your arguments are expressed using quantifiers. Let's move to the second example. Okay. Example number 8. Determine whether the argument is valid or invalid using the Euler diagram. Okay, let's start with the first one. So, first premise. Let's make a diagram. And you have no prime numbers are negative. What do you mean by this? No prime numbers are negative. Going back to our diagram, when you say no x are y, it means that there are two sets with no common point. Okay? So that means that we draw here a circle, and this represents the set of prime numbers, and we draw another set here which represents the set of negative numbers. So no prime numbers are negative. So that's your first premise. What about your second premise? Your second premise is the number n is not negative. It means that your n is not inside the set of negative numbers. But that statement actually implies that your n is either here, right? Okay? That's one possibility. Or your n is, okay, we have a case here where n can be found not only inside the prime number but also outside the prime number. So if this is your prime set of prime number and this is your set of negative numbers, okay, aside from n inside the set of prime, n can also be found outside prime and negative, right? Because your second premise is the number n is not negative. So when you say it is not negative, it means that it's not found inside the negative set of negative numbers, which brings you to two possibilities. That is, either your n is inside the set of prime number or outside the set of prime numbers. Okay? So, let's now look at our conclusion. Is the conclusion consistent with the two diagrams? Okay? It says the number n is a prime number. Oh, that's your conclusion. Is it consistent with the first diagram? The number n is a prime number? Yes, it's consistent. But the question is it consistent with the second diagram? No, it's not consistent anymore. So therefore, because it's not consistent to the second diagram, although it is consistent to the first diagram, but we say that the argument is invalid because your conclusion is not consistent with the two diagrams. Take note, you don't always get two diagrams, no? It depends on the implication of your premises actually. Using the first premise, you have this diagram, but the second premise will lead you to creating another diagram. Okay? And therefore, you have to check whether your conclusion is consistent with the two diagrams. Since it is not consistent with one of the diagrams, then we say that the argument is invalid. Last. Okay, we have some A students. So again, we draw a diagram here. Some A students sit in the front row. Okay, when you say some, this is represented by a diagram where the two sets intersect, right? Okay, so when you say some students sit in the front row, we have two sets here. The first set is the set of A students, and the second set is the set of students sitting at the front row. So this is A students, while this one is students sitting in the front, okay, front row. Yan. Okay, that's for your first premise. What about the second premise? The second premise says all those who sit in the front row, okay, referring to this set, to this particular circle, all those who sit in the front row are attractive. So you have another set here, another circle that is actually bigger than the set of students sitting in the front row, right? Because all those who sit in the front row are attractive. So what do you mean by that? It means that we will draw another circle where the circle for students sitting in the front row is inside. Okay, so the bigger circle here is for attractive students. Okay, or you can also make your circle bigger to contain the A students. That this is still consistent with the second premise. But let's look at now the conclusion. Is the conclusion consistent with our diagram? The conclusion says some A students are attractive. Okay, these are the A students, and the bigger circle here is attractive students. So is it true that some A students are attractive? Obviously yes, because the set for A students intersect with attractive students. So since our conclusion is consistent with the diagram, then we say that this argument is valid. Okay, so thank you and God bless.